So this is the exercise on the previous topic, that is the divisibility. Solve all these problems first. Now we are going to start new topic, that is the congruence relation. Before that, solve all these examples, that is find all prime numbers that divides to 50 factorial and all these problems. Find least common multiple, that is the LCM of these two numbers. Find the greatest common divisor. We can also find the least common multiple by using the formula that's depend on the greatest common divisor. This is the formula. That is the least common multiple. Then this is the notation: square bracket a comma b is mod a into b divided by greatest common divisor of a and b. In round bracket a comma b means what? Greatest. It is first find greatest common divisor and then use this formula to find least common multiple. So solve these problems, all these problems of exercise. Now we are going to start the next topic, congruence relation. The next topic is congruence relation. So this is the next topic, congruence relation. So what is the definition of congruence relation? It is called congruence relation modular. So what is the phrase? That congruence relation modular. And the definition is, suppose a and b are two integers, n is greater than 1. B an integer is also integer, n is also integer. That is the value of n is what? Strictly greater than 1 means value of n is what? 2, 3, 4, 5. Then if n divides to a minus b, then we say a is congruent to b modular. And the notation for a is congruent to b modular denoted by this notation: a, then write 3 lines, b in round bracket modn, and read it as a is congruent to b modular, or a is congruent to b modular. Congruents are congruent to b modular. And so what is the definition? And this relation is called congruence relation modular. The relation is called congruence relation modular. And so that is the definition. Just remember this definition, that a is congruent to b modular if n divides to a minus. If n divides to a minus b, then we say a is congruent to b modular. And you know this is by using this notation, that a, then these 3 lines, b in round bracket modn, read it as a is congruent to b modular. So what is the definition of a is congruent to b modular? If n divides to a minus b, then a is congruent to b modular. So this is the definition. And when we said, we know that when n divides to a minus b, if a minus b expressed in the form n into some integer. Okay. So the definition of congruence relation is also is depend on the definition of divisibility. So here are some examples, that 5 is congruent to 11 module 6. Why? Because 6 divides to 5 minus 11. What is the 5 minus 11? The value of 5 minus 11 is 6. Why is minus 6? And 6, it is minus 6 is divisible by 6. That is 6 divides to 5 minus 11, and therefore 5 is congruent to 11. Similarly, minus 7 is congruent to 10 module 17, because 17 divides to minus 7 minus 10. Minus 7 minus 10 is minus 17 and is divisible by 7. So also some examples, 14 is congruent to minus 4 module 3. Why? Because 3 divides to 14 minus minus 4. Means what? 14 minus minus 4 is what? Is minus 18. So 3 divides to minus 18. Okay. And so we have that 14 is congruent to minus 4 module 3, because 3 divides to 14 minus minus plus 4. Here write first 14 and then minus minus 4, right? That is equal to plus 18. 3 divides to 18. So correction is there. Don't write minus 4 minus 14. Write 14 minus minus 4. 3 divides to 14 minus. Then we done with this. That 14 3 divides to 14 minus minus 4. That is 3 divides to plus 18. And so Why 3 divided to plus 18? Because 18 expressed in the form 3 into 6, and 6 is the integer. 5 is congruent to 5 module 3 because 3 divided to 5 minus 5, that is 0. 5 minus 5 is 0, and 0 is divisible by every number. 3 divides to 0. Why 3 divides to 0? Because 0 expressed in the form 3 into some integer. 0 is the integer. 0 is divisible by every integer, or every integer divides to 0, and therefore 5 is congruent to 5 module 3. A is congruent to A module n for all A and for all n. Every integer is congruent to itself module n. Every integer is congruent to module n. So this is the definition of congruence relation. When we say two numbers are congruent, when A is congruent to B module n, if n divides to A minus. So a very simple definition that the two numbers are congruent. Then example on this important example show that the congruence relation in Z or on Z is an equivalence relation. So we know that when the relation is equivalence relation, if the relation is reflexive, symmetric, and transitive. So the first condition is we have to show this relation, congruence relation is equivalence relation. That is, first we have to show the congruence relation is reflexive. So right here, first the definition of this congruence relation, that A is congruent to B module n if n divides to A minus B. So just first write the definition of the congruence relation. Then first condition, we have to show every integer. We have to show the relation is reflexive, means every integer, every member of this Z related to itself. So take any Z, any element from Z, this capital Z. Suppose A belongs to Z. Then what is A minus A is 0 and is divisible by n. That is, n divides to A minus A, and therefore A is congruent to A module n for any A belongs to Z, and therefore the relation is reflexive because A is congruent to A module n. Why is A is congruent to A module n? A is any integer. Why A is congruent to A module n? Because n divides to A minus A, that is 0. 0 is divisible by every integer, and therefore A is congruent to A module n, and therefore the relation is reflexive. What is the relation? Relation, the notation for relation is what? These three lines. So the notation for relations is what? Either bigger or capital R. Okay. So here the notation for relation is these three lines, or the relation name of the relation is what? Congruence relation. So the congruence relation is reflexive because every integer, every member of the Z related to itself, and therefore the relation is reflexive. So when the relation is reflexive on the set, if every element of the set related to itself, so this Z contains infinitely many elements, and we have to show that every element related to itself. And so we take any element from the Z, suppose A, and here we have A is related to A. Why A is related to A? That is, the relation is congruence relation. A is congruent to A module n because n divides to A minus A, that is 0. N divides. 0 is divisible by every number. Therefore, A is congruent to A module n, and therefore the relation is reflexive. Now we have to show the relation is symmetric. So when the relation is symmetric, if the A is related to B, then if B is related to A, then we say the relation is symmetric. If A is related to B, then we have to show B is also related to A. So I assume that A is related to B. That is, we assume that A is congruent to B module n. And what do I have to show? B is related to A means B is congruent to A module n. So A is congruent to B module n implies what? N divides to A minus B. Okay, by using definition that A is congruent to B module n implies n divides to A minus. But if n divides to A minus B, then n divides to minus in bracket A minus, because if n divides to suppose 5, then n also divides to minus 5. N divides to 5. If n divides to 5, then n also divides to minus 5. So n divides to A minus B implies, or hence we have that n divides to negative of this number, minus A minus in bracket A minus B. and this negative effect of negative, what we have, b minus n divides to b minus c. And so n divides to b minus a implies what? B is congruent to a modulo n. B is congruent to a modulo n because n divides to b minus c, and therefore the relation is symmetric. That is, if a is congruent to b modulo n, then we have b is congruent to a modulo n, and therefore the relation is symmetric. That is, if a is related to b, then we have b is related to a, and therefore the relation is symmetric. Now we have to show the relation, this congruence relation is transitive. So when we say the relation is transitive, any relation is transitive, if the A is related to B and B is related to C, and if we have A is also related to C, then we say the relation is transitive. So I assume that A is related to B and B is related to C. That is, I assume that A is congruent to B modulo n and B is congruent to C modulo n. And now we have to show A is congruent to C modulo n. Then the relation becomes a transitive relation. But what is our assumption? A is congruent to B modulo n implies n divides to A minus, and B is congruent to C modulo n implies n divides to B minus. And we know that if n divides to, suppose x and n divides to y, then n divides to x plus y. This is the property of divisibility. That is, if n divides to, suppose, x and n divides to y, then n divides to x plus y. And so n divides to this number and n divides to this number, we have n divides to addition of these two numbers, a minus b plus b minus c, by using that property of divisibility. And this a minus b plus b minus c becomes a minus c. That is what we have, n divides to a minus c, and therefore a is congruent to c modulo n by using definition of congruence relation. And therefore the relation is, congruence relation is transitive, and hence the congruence relation modulo n is an equivalence relation on Z or in Z, because the congruence relation is reflexive, the congruence relation is symmetric, and the congruence relation is transitive. Therefore, the congruence relation in Z is what? Is an equivalence relation. Similarly, the next problem, some properties of the congruence relation. The first property is what? If A is congruent to B modulo n, then prove that Ax is congruent to Bx modulo n. All these A, B, C, D, X, Y, all these are what? Integers. Then what is the theorem number 4? That A is congruent to B modulo n, then we have to show Ax is congruent to Bx modulo n, and A plus X is congruent to B plus X modulo n. And similarly the B. So the proof of this first A, what is given? A is congruent to B modulo n. So what is it implies? It means that n divides to A minus B, and n divides to A minus B means A minus B expressed in the form n into some integer. So take that integer as k for some k belongs to Z. So this is the definition of divisibility. N divides to A minus B means A minus B expressed in the form n into some integer. That some integer, notation for some integer is, suppose here is k. Then the first, we have to show Ax is congruent to Bx modulo n. So when X is congruent to Bx modulo n, if n divides to Ax minus Bx, and when n divides to Ax minus Bx, if Ax minus Bx expressed in the form n into some integer. So consider Ax minus Bx and try to express this Ax minus Bx as n into some integer. So consider Ax minus Bx. So take this x as common and substitute a minus b as nk, and then what we have, this ax minus bx expressed in the form n into kx, right? This kx in bracket, and this kx is integer because all these k and x are, these both are integers, and multiplication of integer is integer, this is integer, and this implies n divides to ax minus bx because ax minus bx expressed in the form n into some integer, and therefore this n divides to ax minus bx. And therefore Ax is congruent to Bx modulo n, the proof of the first. Also we have to show A is congruent to B modulo n, then A plus X is congruent to B plus X modulo n. So when A plus X is congruent to B plus X modulo n, if n divides to A plus X minus in bracket B plus X, and when n divides to A plus X minus B plus X, if A plus X minus B plus X expressed in the form n into some integer. So consider A plus X minus B plus X and try to express this in the form as n into some integer. So consider A plus X minus B plus X, and then effect of this minus, what we have, plus x and minus x becomes 0. So we have a minus b. And the a value of a minus b by assumption is what? Nk, where k is integer. And therefore, a plus x minus b plus x expressed in the form n into some integer. And therefore, n divides to a plus x minus b plus x. And therefore, a plus x is congruent to b plus x modulo n. Because n divides to a plus x minus b plus x. The proof of this. Similarly, the second theorem B. This is important as far as the exam concerned. That if A is congruent to B modulo n and C is congruent to D modulo n, this is given. And what do I have to show? A plus C is congruent to B plus D, and the second one and the third one. So the first one, this first one and third one are important. So what is given? First, write the meaning of given. So what is given? A is congruent to B modulo n implies n divides to A minus B, and therefore A minus B expressed in the form n into some integer. So use the notation K1 for that. And also given C is congruent to D modulo n, therefore n divides to C minus D, and so C minus D expressed in the form n into some integer. Suppose that integer is K2. Then what we have to show first? We have to show A plus C is congruent to B plus D modulo n. So when A plus C is congruent to B plus D modulo n, if n divides to A plus C minus B plus D. And when n divides to A plus C minus B plus D, if A plus C minus B plus D expressed in the form n into some integer. So we consider A plus C minus B plus D and express this in the form n into some integer. So after negative effect of negative sign, what we have? A minus B plus C minus D. And the value of A minus B is what? Nk1. The value of C minus D is Nk2 by using this equation. And then we take n as common. What we have? K1 plus K2. K1 and K2 are integer. And addition of two integer is integer. Therefore, K1 plus K2 is integer. And this implies this. A plus C minus B plus D expressed in the form n into some integer implies n divides to A plus C minus B plus D. And therefore, A plus C is congruent to B plus D modulo n by using the definition of congruence relation. Now we have to show this A x plus Cy is congruent to Bx plus Dy, where x and y are integers. So consider Ax plus Cy minus Bx plus Dy. Consider Ax plus Cy minus Bx plus Dy. So is what? Ax minus Bx after negative sign, effect of negative sign, plus Cy minus Dy. And then take x as common, y as common. And the value of A minus B is what? By using the assumption Nk1. And the value of C minus D is what? Nk2. Substitute that value. And then take n as common. We have K1x plus K2y, where this K1x plus K2y is integer. So this Ax plus Cy minus Bx plus Dy expressed in the form n into some integer implies n divides to Ax plus Cy minus Bx plus Dy, and therefore Ax plus Cy is congruent to Bx plus Dy modulo n. Now we have to show AC is congruent to BD modulo n. When AC is congruent to BD modulo n, if n divides to AC minus BD, and when n divides to AC minus BD, if AC minus BD expressed in the form n into some integer. So consider AC minus BD, and then value of AC minus BD. So subtract BC and add BC. Here is the adjustment, that is subtract BC, add BC, minus BD as it is, AC as it is. And then they take this C as common from these first two quantities. Here is take B as common from the second one and third one and fourth one. And then we have the value of A minus B by assumption is Nk1. And then the value of C minus D is Nk2. And then take this N as common. Then K1C plus Bk2. And this bracket, the value of this is the integer K1, because all these K1, K2, C, B, all are integers, and addition and multiplication of integer is integer. Therefore, this is integer, and therefore, what we have AC minus BD expressed in the form n into some integer, and therefore, by using definition of divisibility, n divides to AC minus BD, and hence AC is congruent to BD modulo n. So this is the proof of the theorem number A and theorem number B, and that the theorem number B is important as far as the exam concerned. So we will see the next theorem in the next lecture.